Can you all see my screen?
Yeah.
Fantastic. Cool. All right. So hi everyone. So as Zhenfei introduced me, I'm Jun Park. I'm a third year PhD student in the computer science department at Stanford, working with Michael Bernstein and Percy Leong. And today I talk to you about generative agents, interactive simulacra of human behavior. And this is work I developed with my advisors, Michael and Percy, as well as my mentee, Joey O'Brien, and mentors, Mary Morris and Carrie Kai. For over 4 decades now, from the time of cognitive architectures and symbolic systems to statistical machine learning, we, the researchers and practitioners at the intersection of HCI and AI, envision the ability to simulate believable human behavior that is so compelling and so human-like that they provide an illusion of life. Oh, interesting. Seems like my slide wasn't going. Let me try this one more time. Can you see my slide sort of changing on your screen?
Yeah, it works.
So hopefully this time it works. Cool. In our vision, this ability, if achieved, promised a new class of interactive applications ranging from model human processors for usability testing to social robots, NPCs, and ubiquitous computing applications that require a rich understanding of human cognition, and even to the foundation of small and large-scale social simulations that would test social science and economics theories that are difficult to implement in real life. But despite their wide application spaces, we faced fundamental challenges when simulating human behavior. The space of possibility in the way we behave and communicate, we found, was much too vast and too complex to navigate with existing methods. But I see a new opportunity that is emerging. Generative models such as large language models that are being trained today are trained on broad data that reflect our lives, like the traces on our social web, Wikipedia, and more. So as a result of that, these models encode a tremendous amount about us, how we live, talk, and behave. So I posit that with the right method, they can be transformed into the core ingredient that had been missing in the past decades that will enable us to simulate believable human behavior. Today, I will introduce a new way of simulating human behavior in fully general computational agents that can populate an open world like ours, while ensuring long-term coherence by fusing a large language model with a novel agent architecture that remembers, reflects, and plans based on constantly growing memories and cascading social dynamics. These agents, I will demonstrate, can not only plan and lead a believable day in life where they wake up in the morning, do their routines, and go to work as individuals in a sandbox game environment, but they can also come together to give birth to an entirely artificial society of their own, like the one you see here, where each agent will have their own subjective memory and experience and spread information, form relationships, and coordinate amongst each other before reflecting on the past days and deciding on how they will live tomorrow. These are generative agents. And these generative agents, I'm going to suggest, open up a new genre of human-AI interaction that is fueled by our newfound ability to simulate believable human behavior. So with that, let me demonstrate to you in more detail Smallville. So this is the setting of our demonstration for generative agents and the mode of agent interaction that takes place in it. Smallville is a sandbox game environment that we developed featuring the common affordances of a small village, ranging from houses, apartments, cafe, bars, schools, stores, and the sub-areas and objects that make the space functional, like the bathroom, kitchen, and common room in a family house, and a bookshelf and a table in the common room. And we populated this space with 25 generative agents and initialized each of them with one paragraph of natural language description to depict each agent's identity, including their occupation and relationship with other agents, and seeded this paragraph into the agent's memory at the start of the simulation. And that is it. That is all the input that we ever give to these agents. And these agents interact with their environment through their actions based on their own volition. And here's how this works in Smallville. First, the agents generate a natural language statement describing their current action, such as Isabella Rodriguez is drinking coffee. They then translate this into concrete movements that affect the sandbox game environment, along with the automatically generated emojis that visually describe the agent's actions, and they influence the state of the objects in this world. So a bed can be occupied when an agent is sleeping, and a refrigerator can be empty when an agent uses up the ingredients to make breakfast. To interact with each other, they determine whether they want to engage in conversations when they see another agent, and they generate natural language dialogue if they decide to engage. So this is a good example here. This is between Isabella and Tom, who are talking about Sam Moore, who is a fellow agent in Smallville, initiated with a memory that he is running for a local mayor. Here, Isabella says, I'm still weighing my options, but I've been discussing the election with Sam Moore. What are your thoughts on him? And Tom responds, to be honest, I don't like Sam Moore. I think he's out of touch with the community and doesn't have our best interest at heart. And importantly, the users can also influence and interact with these agents. First, much like how agents form dialogue with each other, a user can engage in a dialogue with these agents by specifying a persona that the agent should perceive them as. For instance, if the user specifies that they are a news reporter and asks about the upcoming election in Smallville, who is running for office, Isabella might reply, Sam. Or to directly command one of the agents, the user can take on the persona of the agent's inner voice, and this makes the agent more likely to treat the statement as a directive. So if the user tells John that he is now running for office while taking the persona of John's inner voice, John would decide to run in the election and share his candidacy with his wife and son. And second, just as agents can, the user can alter the state of the agent's environment. For instance, if the user sets Isabella's toast on fire, Isabella would rush to put out the fire and remake her toast. And finally, the user can actually control an agent by embodying an agent already present in the world, such as Isabella and John or Joan as an outside visitor. The inhabitants of Smallville will treat the user-controlled agent no differently than they treat each other. They will recognize its presence, initiate interactions, and remember its behavior before forming opinions about it. Okay. Now, let me dive deeper and present you with some vignettes from Smallville that describe their individual as well as collective emergent behaviors. As individuals, generative agents create daily plans that reflect their experiences, execute those plans, react, and replan when appropriate. Here's an example day in the life of the Lin family. So you see the Lin family on the map right there. And the Lin family is a family of three: the mother, May, who is a college professor, the father, John, who is a store clerk at the local pharmacy, and the son, Eddie, who is a student at the college who studies music theory. In the Lin family, John is the first to wake up at 6 a.m. He brushes his teeth, takes a shower, cooks breakfast. And throughout the morning, other family members follow suit, catch up with each other, and by 8 a.m., head out to their respective workplaces. So May and Eddie to the college, and John to the pharmacy. Let's eavesdrop on them a little bit to get a sense of what they're talking about. Again, their movements, decision to engage in the dialogue, and the dialogue themselves are all generated. So nothing you see here is hard-coded. So here, John and Eddie are catching up in the morning. John says, "Good morning, Eddie," and Eddie responds, "Good morning, Dad." And John asks, "What are you working on today?" And Eddie responds, "I'm working on a new music composition." And only a little after that conversation, May wakes up and joins John. By now, Eddie already left for his classes, but John recalls a conversation he and his son just had and finds that to be relevant here. He updates May that Eddie is working on a new music composition for his class, and May responds, "Oh, that's wonderful." And meanwhile, as a collective in this practically a small society of generative agents, these agents exhibit emergent social dynamics where new relationships form, information diffuses, and coordination arises. Let me go over these emergent behaviors. First, information diffuses across the agent community. We've sort of already seen a glimpse of this with the Lin family, but here's another example. We see the Sam with a memory that he's running for a local election, and he's telling everyone about it throughout the day. Here, he tells Tom, I'm actually running for mayor in the upcoming election, and Tom says, really? That's great news. And a few hours later in the game world, John and Tom, who are colleagues at the local pharmacy and store and have independently heard about Sam's candidacy, talk to each other about Sam's chances of winning. John says, I heard that Sam Moore is running for mayor. Do you think he has a good chance of winning? And Tom responds, I think he'll get a lot of support. Second, new relationships form among the agents in Smallville. Here's an example. LaToya and Sam do not know each other at the start of the simulation, but while taking a walk in Johnston Park, Sam runs into LaToya and they introduce themselves. LaToya tells him that she is at the park to take some photos for a project that she's working on. And the next day, when Sam sees LaToya again, he and LaToya remember each other. This time, Sam asks LaToya, how is your project going? Finally, agent coordination emerges in Smallville. In our demonstration, we set the starting date to be on February 13th. And with Isabella, who is the owner of Hop's Cafe, we seeded an intent to plan a Valentine's Day party from 5 to 7 p.m. on February 14th. From that seed alone, Isabella invites friends and customers to the party, spends the day, the afternoon of the 13th, decorating the cafe for the occasion, and enlists Maria, who is a friend and a frequent customer at the cafe, for help. And meanwhile, Maria asks Klaus, who is her secret crush, to go to the party with her. And on the day of Valentine's, 5 agents, including Klaus and Maria, actually show up at Hop's Cafe at 5 p.m. and they enjoy the festivities. Okay. So, how do we do this? How do we achieve this agent behavior? Our main contribution in this work is basically this architecture represented in this figure. This is the architecture of generative agents that powers each of these agents in Smallville. At the center of this architecture is what we call the memory stream. This is the primary database that maintains a comprehensive record of an agent's experience in natural language. From the memory stream, records are retrieved as relevant to the agent's cognitive processes. Let me go over the modules of this architecture in just a little bit more detail. So first is the memory and retrieval. Here's the challenge that we're trying to overcome with this module. Generative agents in Smallville and likely beyond accrue an extremely large set of records in their memory stream. And fitting the entire memory stream to a large language model can distract the model. And today, not even a few hours worth of memory in Smallville can fit into the limited context window of the state-of-the-art language model. Our agents, therefore, need a way to store and selectively retrieve portions of their memory, and that is the aim of the memory stream and the retrieval function. So here's a tip of the memory stream for the agent Isabella. And on the right, you see a few example memory objects in the stream that contain a piece of memory described in natural language with a creation time timestamp. In particular here, what you're seeing are observational memory of Isabella. And based on this memory stream, our architecture implements a retrieval function that takes the agent's current situation as input and returns a subset of the memory stream to pass onto the language model, which then generates the final output behavior of the agent. So in this example, if the situation that Isabella is trying to react to is someone asking, what are you looking forward to the most right now? She would retrieve things that are about the party and formulate a response. I'm looking forward to the Valentine's Day party. Here's how this works. In our architecture, we designed the retrieval function as a combination of the recency, importance, and relevance function for each piece of memory. So basically, we bias towards retrieving memories that are recent, important, and relevant to the current situation. In our work, the recency function is implemented as an exponential decay function. the importance function is a prompt that asks the language model for an event saliency. And the relevance function is a cosine similarity measure of the embeddings of the query sentence and the description of a memory. Now, what we noticed in our work is that with just a raw observational memory, though, our agents struggle to generalize or make inferences. So periodically, we summarize clusters of records in agents' memory stream into higher level abstract thoughts that we call reflections. And importantly, once they are synthesized, these reflections are just a type of memory. So they are stored in the memory stream, just like the observational memories that you've seen previously. Here's the way we do this. First, we generate questions on what to reflect on by looking at 100 most recent records in the agent's memory stream. So if an agent just had lunch, it could be something like, what does the agent like to eat? Then we retrieve records that are relevant to answering those questions, which might be things like, the agent ate an omelet today, yesterday, and the day before yesterday, and we summarize that into a reflection. Maybe the agent likes to eat omelets. Over time, what this generates is basically these trees of reflections. The leaf nodes are observations, and the non-leaf nodes are thoughts that become higher level, higher up the tree they are. So here's an example for Klaus. Klaus is a student researcher who studies social science and sociology. So he does research around urbanization and gentrification and so forth. What you see at the very bottom of this tree are observational memories, like Klaus is reading about gentrification or about urban design. And you basically see those getting summarized into reflection that says something like, oh, he spends many hours reading. That in turn gets summarized and merged with other reflections and observations to create higher level reflections, like he's engaged in research activities and he's highly dedicated to research. So I think somebody might be unmuted. Ah, perfect. Thank you. Finally, while a large language model can generate plausible behavior in response to situational information, we find that optimizing for believability in the moment can sacrifice believability over time. What we needed was for the agents to plan over a longer time horizon. So plans describe a future sequence of actions for an agent and help keep the agent's behavior consistent over time. For instance, for Klaus, who is a student researcher dedicated in his research and has an impending deadline, he would generate plans to spend his day working at his desk, drafting his research paper. In our work, we generate the plans by prompting a large language model with a prompt that summarizes the agent and the agent's current status, as you see here for Eddie. So you basically see at the top of this prompt, we might have something about who Eddie is, right? We see his name, his age, some traits that he has, like personality and summary of his past experiences. And down below, you see things like, oh, where he is right now, what his plans were, is there anything that he would need to react to, and so forth. So his current status. Now, a challenge here, however, is controlling for the granularity of the plans that are being generated. In our work, we control for this by taking a top-down approach where we recursively generate more details in the plan. So here's an example. On the left-hand side is Eddie's plan generated in broad strokes that divides his days into roughly 7 chunks. We then decompose these chunks first into hourly schedule, and then into 5 to 15-minute actions that you see on the right-hand side. Once we reach the desired granularity in the agent's schedule, they can simply act out their plans in the game world. In sort of our use case for like the game simulation and demonstration, 5 to 15 minutes was a good chunk. It seemed believable, and also sort of in terms of cost benefit analysis, this sort of makes sense. But depending on what application you're trying to run, what is really nice about this recursive format is you can go extreme either way. So you can create not just a daily plan, but weekly plans or yearly plans to make even larger chunks of plans. Or you can decompose them even further to basically plan minute-by-minute sequences as you need. Okay? But sometimes the agents may need to change their plans. For instance, if Eddie's father, John, records that he sees Eddie taking a short walk in the house garden, he might decide to start an impromptu conversation. And we would prompt our large language model, as shown here, to make this determination and edit the agent's plans if the situation calls for their responses. Okay. So I described to you our agent's behavior and architecture, basically how we built these agents. Now we can ask, how do we evaluate these agents? The main dependent variable that we use is what we call believability, which has been a central design and engineering goal in a long line of prior literature. So basically the question here is, do agents remember, plan, act, react, and reflect in a believable manner? So it's kind of like a Turing test, but in a behavioral setting. And to evaluate generative agents' believability, we leverage a methodological opportunity by interviewing it in natural language. In particular, we craft 5 categories of questions, 5 questions each, where to respond to these questions properly, the agents must successfully retrieve and summarize information to stay in character, remember, plan, react, and reflect accurately. So here are some example questions and answers from Klaus's interview. When we asked him to give an introduction of himself, he properly recalled his name, characteristics like his age, what he does, what he studies, and so forth. And when we asked him what he would do when his breakfast is burning, he tells us that he would quickly turn off the stove and make sure the food doesn't continue burning. Our study procedure for this was as follows. So we test our generative agents architecture as well as ablated architectures and human authors to answer these questions. We then asked 100 human evaluators to rank the answers from different conditions. Then we calculated true skill rating for each of these conditions, which is a generalization of the ELO rating system. Here's what we find. What we find is that the components of our agent architecture, observation, plan, and reflection, each contribute critically to the believability of the agent behavior. So the red bar you see is the performance of our full agent architecture, and it significantly outperforms basically every other condition you see here, including the human author baseline. It's also worth noting that when compared to the condition representing prior work, so imagine that just being ChatGPT, which is the no reflection, plan, and observation condition, our full generative agent architecture produces a standardized effect size of cohency equal to 8.16. Another way of saying that is that's 8 standard deviation difference in performance between what ChatGPT can do in this environment compared to our agent architecture. Okay. Of course, I would note here that this did not mean that our agents were without flaws. They would sometimes fail to retrieve certain memories, like when Rajiv answered, I haven't been following the election too closely, even though he talked to Sam to hear about his candidacy. And they would sometimes embellish their memory too. For instance, if Isabella was aware of Sam's candidacy in the election, and she confirmed this when she was asked, but she also added that he's going to make an announcement tomorrow, even though Sam had mentioned no such plan, and he was not planning to do that. So these are not perfect. Additionally, we conducted an end-to-end evaluation of the agents to better understand the types of emergent community behavior we observe among generative agents. First, we find that agents shared and remembered information. 7 agents heard about Sam's candidacy, and 12 agents heard about the Valentine's Day party. You can actually see the path the party invitation took across the agent community on the right here. So you basically see Isabella saying, hey, I'm planning a Valentine's Day party at Hop's Cafe. Would you like to come? And this gets to Giorgio, Eddie, Sam, and they each now then go and tell this about their friends and families. So for instance, Sam tells this to Jennifer, who is his spouse. He tells her that, speaking of which, Isabella has invited us to a Valentine's Day party at Hops Cafe. Second, we find that the agents remembered and joined the Valentine's Day party. So in particular, 5 agents came to the party. Of the ones who didn't make it, 3 cited conflicts, like Rajiv, who is a painter, who explained that he was too busy to come. And 4 showed interest in the party, but still did not show up. Now, this does make things difficult to evaluate, though, because on one hand, we might view that as an error, but on the other hand, this is extremely realistic human behavior in my experience. But of course, there were boundaries and errors in our agent's behavior. One that is particularly noteworthy here is that the instruction tuning of the language models seems to guide the behavior of the agents to be overly polite and cooperative. Even when talking to her family, for instance, May always greeted them in a very formal way, and Isabella never really refused any ideas to include in her party, even when the ideas did not exactly align with her identity. Okay. So that's generative agents. And sort of I guess this is from back in April, but this project in particular has gotten a surprising amount of interest from both the academia as well as the public, and we've been reflecting on why. And ultimately, I think one of the reasons why this project has gained the amount of interest that it has gotten is because the application space for something like generative agents is quite vast. So before I end my talk today, I'm going to highlight perhaps one application space that I think is particularly interesting for me, at least. And that's called social simulacra. So again, this is the work that I developed with my advisors, Michael and Percy, as well as my mentee, Lindsay Kopowski, and mentors, Mary Morris and Carrie Kai. And you might recognize that this is actually work that was published last year. So this actually predates generative agents. What you'll see is with this work, we didn't really have all the agent architecture put together. So when we say agent in social simulacra, we really just mean prompting a large language model with a maybe chain of prompts or a few short prompts. So clearly, in terms of technique, much simpler. But you sort of see the philosophy of simulating human behavior connecting to this work. And you can imagine sort of how this kind of work could be even more powerful if we have something like generative agents going forward. So let me quickly share this. The problem space here is this. For many decades now, we have designed and deployed countless social computing systems. But the irony is, even today, as more and more people populate these systems, we continue to get surprised by the things that happen in them, like unexpected trolling or sort of antisocial behaviors, all the way to cases such as people congregating to spread hate speech and misinformation. But why is this? Because in theory, this issue of understanding how people might use an interactive system is something that we know how to tackle. And that's what prototypes like the ones you see here are all about. But here's the challenge. In my vision, a successful social computing prototype needs to prototype not, for instance, the user flow of how one might click around different pages, but the social dynamics that might arise when the system reaches critical mass of users, because that's where the uncertainty is in social systems. And that is an impossible task for our existing approaches. Where are we going to get thousands or even tens of thousands of diverse test users? How would we prototype the social dynamics that might arise without releasing these designs to a large number of people? Generative agents enables a new way of prototyping social computing system that tackles this challenge by generating a large number of synthetic social interactions that might arise in a populated social system. And we call this social simulacra. Social simulacra is an approach. It is an approach of leveraging the richness and the generative capacity of models such as a large language model to populate a social computing system with generative agents and behaviors for the purpose of prototyping the system design. And we will demonstrate this approach in practice by implementing it as a web application tool for prototyping subreddits that takes community design such as the goals, rules, and moderation strategies as input, and translates them into a generated community like the one you see here that has never existed before to illustrate the good, the bad, and the ugly of the interactions that a community governed by these designs may harbor. Now, here's what this tool can in particular do for the designers. Our tool has three core features. One is generate, the other is what if, and the final one is multiverse. And they each answer to the core needs in social computing design. So first, generate. Prior literature suggests that social computing designers struggle to envision the breadth of interactions that their design might facilitate. Generate helps the designers by populating a subreddit community with generated users, top-level posts, and replies to those posts to help them envision this space. So it takes from the designer a range of design specifications, such as the goals, rules, and member composition of a community, and returns a subreddit-like page that is now fully populated, like the one you see here on the right-hand side. Here's an example here. In these slides, everything on the left is the designer's input, and everything on the right is Social Simulacra's output. So in a community for connecting people moving to Los Angeles with locals, Social Simulacra generated a new user, Leon Santos, who posted, "I'm new to LA. What are some of the best places to visit on a weekend?" And in response, our tool generated Lucas Jameson, who replied, "I would recommend visiting the Getty Center, the Museum of Contemporary Art, and going hiking." Here's another one. This time in a community for people interested in learning about personal finance, Social Simulacra generated Dane Wood, who posted, "I spent $21K to go to college and ended up with $23K in debt." But in response this time, our tool generated Elizabeth Neal, who is a troll. Here she said, "That's a lot of debt, man. I haven't seen that much since I shopped at Macy's during the holiday season." There you go. The second feature, What If, aims to give the designers more interactive control over Social Simulacra to help them explore how individual conversation might be influenced. So What If takes from the designer an existing Reddit conversation and regenerates it from the middle of it, as you can see here. So imagine Maya Smith posted to a forum for WIST authors. She said, "I've been working on my WIST paper for a few weeks and I'm feeling really stuck." And to this, Heather Hernandez, who is a human-computer interaction professor, replied with a short advice. "It's normal to feel stuck when writing a paper. Good luck." But as a designer, you might want to know so you can prepare for it. What if, instead of Heather, a troll replied? Or what about an advertiser? The What If feature answers to that particular need. So here, instead of Heather, a troll replied, "You're just not cut out for this kind of research." Whereas here, an advertiser replied, "We click the link below to learn more." Equipped with this, the designer can now even ask, what could the moderator say in response to this undesirable behavior? And if the moderator intervened with no advertisements please to the advertiser, what are some of the ways the conversation could have developed from that point on? And the final feature is multiverse. And this is the feature that makes the model uncertainty explicit. With the first two features, generate and what if, what I've shown you is our tool's capacity for generating realistic content. But human behavior is inherently complex. And no matter how likely something is to happen, there's no guarantee that it will happen. And this is an important conceptual scaffold for social simulacra, but more broadly for generative agents. So instead of just showing the designer one possible outcome, multiverse augments the previous two features, simulate and what if, by explicitly showing many possible ways the interaction can unfold from one initial state. This encourages the designer to explore the design space with inductive insights, rather than over-relying on the one prediction that was made by the model. So we conducted two sets of evaluation for this work, I'll actually skip the technical evaluation. It basically reads very similarly to the evaluation that I've shown you for generative agents. But I want to share with you the designer evaluation. This is where we actually gave social simulacra to the designers and try to see where this actually helps them design new spaces. Okay. So for this evaluation, what we've done is we recruited 16 participants who actually had experience designing social spaces. So they were either employees at social computing companies, like a lot of social media companies, for instance, or people who have taken courses or studied designing these social spaces online. And we asked them to design a new subreddit with the help of social simulacra. What we find is that today, without social simulacra, the design practices for social computing systems are reactive. So participant 8's comment is particularly salient, which says, basically, all the rules are set in reaction to some dumpster fire. And our participants saw this as the reason why social simulacra could be really valuable, because it would offer them a sense of security if they could try different iterations of established norms before actually releasing their design. We also find that social simulacra offer concrete design insights to our participants. Among them are finding unexpected model citizen behaviors, like impromptu friend seeking to go sightseeing in a community for sharing fun events around Pittsburgh, and finding unexpected undesirable behaviors, like troll farms shifting the tone of a discussion community. So that concludes my talk, and I thank my advisors, collaborators, and funders one more time, and thank you all for having me.